Hello, my name is Gary Tsai. I'm enrolled in EECS 203 at the University of Michigan. Today I will be teaching you about equivalence and validity for quantified logical expressions. Statements involving predicates and quantifiers are logically equivalent if and only if they have the same truth value regardless of which predicates are substituted into the statements and which domain of discourse is used for the variables in the propositional functions. We express such a logical equivalency with the notation S is logically equivalent to T. One such example of a non-quantified equivalency is the statement P implies Q is logically equivalent to not Q implies not P. We will show that these two statements are logically equivalent by showing that they hold the same truth values. In this truth table, we will assign values of true and false to both P and Q. We can evaluate the negations of P and Q by giving them the opposite truth values in each row. P implies Q is false only when P is true and Q is false. For all other cases, P implies Q is true. The same holds for not Q implies not P. It is only false when not Q is true and not P is false. Since these two statements have the same truth values, we can conclude, therefore, that P implies Q is logically equivalent to not Q implies not P. As it turns out, this concept of equivalency also applies to quantified logical statements. Take, for instance, the statement, for all x, P of x and Q of x. This statement is logically equivalent to the statement for all x, P of x, and Q of x, and for all x, Q of x. This statement says that you can distribute a universal quantifier over a conjunction and the logical expression will still have the same truth values. To show that this is true, we have to show that both of these statements always take the same truth value, regardless of what the predicates P and Q are. In order to do this, we need to prove that if for all x, P of x and Q of x is true, then for all x, P of x and for all x, Q of x is true. Conversely, we have to prove that for all x, P of x, and for all x, Q of x is true, then for all x, P of x, and Q of x must also be true. Suppose that for all x, P of x, and Q of x is true. Since the conjunction is true, we know that both for all x, P of x, and for all x, Q of x are true. Because P of x and Q of x are true for every element of x in the domain of x, we can say that P of x and Q of x are true for an arbitrary value of x that we will call A. Thus, P of A and Q of A are true. Now let us prove the converse and suppose that for all x, p of x, and for all x, q of x is true. For this to be the case, both for all x, p of x, and for all x, q of x must be true. If A is in the domain, then we can say that both p of A and q of A are true. Since for all A, p of A and q of A is true, it follows that for all x, p of x and q of x is true. We have just shown that for all x, p of x and for all x, q of x is logically equivalent to for all x, p of x and q of x is true. Equivalents for quantified logical expressions play an important role in logic. Given a certain set of information, equivalence can allow us to assert that other logical statements must hold. This concludes our presentation.